Hello students and welcome to my channel Maths Hub. So in my last few videos I have taken up the topic of lattice. So in my last video I talked about complemented lattice and distributive lattice, and in today's video I'll talk about a modular lattice. So let's see what is the definition of a modular lattice. And we will also try some examples of how to check whether a given lattice is modular or not. So the definition of a modular lattice says a lattice L with the less than equal to relation is called modular if for all ABC belonging to L, A join B meet C is equal to A join B meet C whenever A is less than equal to C. So you can see that the left hand side is same as the distributive law, but on the right hand side the law becomes a little different in case of modular. It becomes A join B meet C. And then there is an added feature over here that A should be less than equal to C, right? So this feature was not there in case of a distributive lattice. So this condition is important. So any lattice will be called modular when for all the elements A, B, C belonging to L, A join B meet C is equal to A join B meet C whenever A is less than equal to C. So now let's see some example, and before we move on to some example, let's do a standard result. This is a theorem which says that every distributive lattice is always modular. So that means let us see how to prove this. So what is given to us? We are given that L with less than equal to is a coset, and this coset is a distributive lattice, right? So if it is a distributive lattice, that means for all the elements A, B and C belonging to L, it will satisfy the distributive law, right? Now, we have to show that every distributive lattice is modular. So for modular, let us pick any three elements. Let A, B and C belong to L, right? Now for modular, we know that the condition should be that A should be less than equal to. Now let's see that how will I get the modular relation. Since it is given that L is distributive, so it will satisfy the distributive property. And if ABC belongs to L, the distributive property says A join B meet C is equal to A join B meet with A join C, right? Now, so this is the distributive law, right? So now one relation is given to us that the element A is at a lower rank than the element C. So according to the Hayes diagram, suppose A is below C, if this is the situation, and this is actually the situation because A is less than C, right? So what will happen to the composition A join C? What is A join C? A join C, A upper bound, the least upper bound of A join C will be C. So that means in the next step, I can replace the term A join C with C itself. And is it proving the modular property? So this was what the modular definition said, that for if ABC belonging to L, if A join B meet C is same as A join B meet C, then it is modular, right? So hence this shows that L with less than equal to is a modular lattice, right? So that means if any lattice comes for checking that whether it is modular or not, if it is distributive, it will automatically become modular, right? So the problem is where it is not a distributive lattice. And yesterday we have also seen that how to check for a distributive lattice. If in a lattice, if for every element there is at most one complement, then that lattice is said to be distributive, right? So, and if you are able to check that the lattice is distributive, then 100% it will be modular. So the problem arises only when it is not a distributive lattice. Then you have to check for all the pair of elements A, B, C belonging to L with this condition. It should obey the modular property. That is A join B meet C is equal to A join B meet with. Right. So let us check one example, and this is also that every modular lattice may or may not be distributive, right? So every distributive lattice is always modular, but the converse is not true. Every modular lattice may or may not be distributive, right? Similarly, there is one more remark. The sublattice of a modular lattice is always modular, right? So if you take a subset from a modular lattice, that will always act as a modular lattice itself, right? Okay. So now let's move on to one of the exercises. You have to show that the diamond lattice is modular, right? And we have already done the diamond lattice. So this is the diamond lattice. And you can see in my video, the same lattice has been done in distributive lattice also. And we have proved that the diamond lattice is not distributive, right? You can check my previous videos on distributive lattice, and you will find that this lattice was proof that it was not a distributive lattice. If it was distributive, it will 100% become modular, right? So now this is not distributive. So let us check why is it modular? Is it modular or not, right? So now when we have to pick the elements A, B and C, any elements A, B and C, we have to keep in mind that the relationship between the first and the third element, how it should be? It should be that the first element should be less than the third element. There is no discrepancy about the second one, but the relationship between the first and the third element is like this. So we have to pick up the pairs in such a way that the first element is always lesser than the third element, right? So now let us take the first pair. Now you can see that E is always less than A, right? E is less than A. So let's choose this inequality and let us choose the pairs. So how can you take one pair? You can take the pair as EBA. This can be one pair, right? Then you can choose the next pair as ECA. Then you can choose the next pair as ED and A, right? So we have these three pairs with me, right? Because I have inserted B, I have inserted C in between, and I have inserted D. In all the three cases, you can see that the first element is less than the third element, right? So now let's check the modular property. So according to the modular property, E join B meet A should be equal to E join B meet with A, right? This is what I should obtain. So let us check whether the left hand side and the right hand sides are giving me the same term. So from the Hayes diagram, what is B meet A? What is the greatest lower bound of B and A? It is E. So E join E is 100% E. Now let's come to the right hand side. What is E join B? Join means the least upper bound. So E join B is B. And what is B meet A? B meet A. B meet A is E. So we are getting left hand side is equal to the right hand side, right? So the first pair is satisfying the modular condition. Now, but we have to check for all the pairs. Now let us take up the next pair as E, C and A. And the same thing we are going to do again. E join C meet A, this left hand side should be equal to E join C meet with A, right? So now what is C meet A? According to the Hayes diagram, C meet A is nothing but E. So what is E join E? It is E itself. Now let's come to the next one. What is E join C? E join C is C. And what is C meet A? C meet A is again. So you can see that the left hand side and the right hand side in the second pair is also coming out to be right. Now let's pick up the third pair. So I'll just highlight the pairs for you. So now let's pick up the third pair of elements and check the same property. So we have E join So we have E join B meet A, and we have to prove it equal to the right hand side. That is E join B meet with A, right? So now what is D meet A? D meet A is A. And what is E join A? E join A is A. Now what is E join D? E join D is D, and then we have D meet A. What is D meet A? It is A, right? So when we had E less than equal to A, we have proven that all the three cases are working well. So now let's choose some other pairs, right? So we have exhausted till now three pairs of elements, right? So now let's move to the next pair. So I have taken E less than B, E less than A. Now let me choose some other pair. Let me now take E less than equal to B now. Let me choose this. So what pairs can I take? I can take the pair EAB. I can take the pair ECB, and I can take the pair. Let me just highlight them. And let me take the next pair as E, B and B, right? So now with the first pair with E less than equal to B, let us check the modular property. E join, okay, let's take it here. E join A meet B, so it should be equal to the right hand side. E join A meet with B. So what is A meet B? A meet B is E. So E join E will give you E. Now what is E join A on the right hand side? E join A is A. And what is A meet B? A meet B is same as E. So we are getting the same thing, right? Let's take up the next pair, E, C and B. E join C meet B and E join C, this will be E join C meet with B. So now what is C meet B? It is A, E, and E join E is E. And what is E join C? E join C is C. C meet B. C meet B is again E. So we are getting E and E are same. So now let's do the third pair with the inequality E less than equal to B. So we have E join D meet B. And on the right hand side we have E join D meet with B. Now this is E join. What is D meet B? D meet B is B itself. And what is E join B? It is B. What is on the right hand side? What is E join D? E join D is D. D meet B. D meet B is same as B. So you can see that for the third pair also, the modular law is satisfied, right? Now, let's pick up the next pair. So what can be the next pair? Now we can choose E less than equal to C now, right? And which elements we can pick up now? We can pick up EAC, we can pick up EBC, and we can pick up ED and C, right? So you can check the same property and you will find that this is E join A meet C, and right hand side is E join A meet with C. E join A meet C is E and E join E is E. Now what is E join A on the right hand side? E join A is A and A meet C is E. So again E and E are coming out to be equal. Now let's take EBC pair now. For EBC pair, you should be having E join B meet C should be equal to E join B meet with C. Now this is E join. What is B meet C? It is E, and E join E is E itself. Now what is E join B? E join B is B, and B meet C is E again. So again we are getting E and E. Now let's check with EDC. So you have E join D meet C, and we have E join D meet with C. So this is E join D meet C is C. And what is E join C? It is C. What is E join D? It is D. And D meet C is C. Right? So now, next pairs. So likewise, when you continue like this, you will find that with all the pair of elements, it will satisfy the modular law, right? It will go a little lengthy, but the procedure for checking whether it is modular remains the same. So it is not difficult, but it is a lengthy process, right? So now after that, you can pick up the pair A less than D, then B less than D, then C less than D, and you can insert the third element, anyone, right? So if you pick up A less than equal to D, then how can you make the pairs? You can make the pair as ABD, you can make the pair as ACD, and you can make the pair as AE and D. Similarly, when you pick up the pair B less than equal to D, you can choose the pair as BAD, you can make it as BED, and you can make it as BC and D. Similarly, you can take inequality C less than equal to D, and you can make the pairing CAD, then CBD, and then CE and D, right? And likewise, you can now also pick up the pair E less than equal to D, right? E less than equal to D. If E is less than equal to D, then which pairs you can make? You can make EAD, you can make EBD, and you can make EC. That means how many inequalities we had? 1, 2, 3, 4, 5, 6, 7. So 7 into 3, 21 cases, right? So you have to check all these 21 cases, and then you will find that this lattice is modular, right? So I'm just leaving it because it is just a repetition. So you can try for all these pair of elements and you can check that it is a modular, right? Okay. Let's try one more problem. So we have to show that the pentagonal lattice is not modular. So this is your pentagonal lattice, and it is easy to check it is not modular because you have to pick up one pair which is not satisfying the modular condition, right? So if you are able to pick up that pair, then automatically you will be easy to prove that it is not modular. So let us take the elements, the inequality A less than equal to C, right? If A is less than equal to C, let's pick up the pair A, O and C. If it is A, O and C, then let's check the modular property. It is A join O meet C, and on the right hand side we have A join O meet with C, right? Now, what is O meet C? It is O. And what is A join O? It is empty set. You cannot join A and O, they're lying on the same line, right? Similarly, what is A join O? It is an empty set. Meet C. So it is what? I cannot further find it out because phi is not present in this element, right? So this is showing that it is not modular, right? I hope it is clear, right? Okay. So thank you so much, and do subscribe my channel WhatsApp, and do comment, and please like if you think the content is good, and believe in yourself and you will be able to succeed. Thank you so much.